I'm a mathematics major at Carroll College, and for my senior project, I looked into applications of the Fourier transform, specifically in modeling sound, in particular the human voice. Now, before we get into definitions, I want to show you a couple of things. So, for now, I'll just have you watch and listen. Alright, and now we'll play that one more time. Alright, so what did we just see? Well, in the first visualization, we saw some waveforms. You might have noticed the amplitude increase during the louder sections, or perhaps you even noticed the speed of the oscillations vary as the different notes were played. Now this first visualization shows us position over time, which is directly related to how the sound is recorded and processed in the first place. But this second visualization perhaps corresponds more closely to our experience of sound, because we can see the different notes played in different places, where the loudness is represented by the intensity of the color. Now indeed, this second visualization is a frequency over time plot. So we have frequency on the vertical axis and time on the horizontal axis. And even if I zoom out, it even looks as if the musical score was painted onto the computer screen. But I assure you that this program has no access to the musical score. So the question at this point is, how did we get from a position over time plot to a frequency over time plot? And now is a good time to fill in some background. So, Joseph Fourier was a French mathematician in the late 18th and early 19th century. In his life, he contributed a lot to what we know about heat transfer today, but his contributions in that field have spilled over to many other fields, including sound. And one of his most important contributions, at least most fundamental, is Fourier's theorem, which states that any continuous periodic function can be expressed as a sum of sines and cosines. Now, this might be pretty unintuitive when we consider examples such as when we consider waveforms such as the sawtooth wave or the square wave or the triangle wave, but indeed each of these has its own formulation in terms of sines and cosines. And we won't go over that formulation in this presentation, but if we know that these can be represented in that way, then certainly we can imagine audio data being represented in that way. So, in addition to Fourier's theorem, we also have Fourier's transform. So if you understand nothing else about the Fourier transform, it's important to know that it takes position over time data, position over time functions, and turns them into magnitude over frequency functions. So you can see that there are two sort of oscillations contained in this first plot. So there's this larger oscillation with a lower frequency, and now that corresponds to, here's our frequency on the horizontal axis, that corresponds to this larger lower spike. And there's also a smaller oscillation that's more frequent, and this corresponds to this higher frequency spike. And now also their amplitude corresponds roughly to the peak of each spike. Okay, so in mathematical terms, this is basically a set of inner products where the our the omega is our frequency variable. And now as our omega value approaches one of the frequencies contained in our function, the orthogonality between these two functions decreases, and so their inner product is resolved to a non-zero value. So you see it's zero pretty much everywhere else except for getting around to the frequencies contained in this function. Now another way to think about it is from a physics standpoint. So an analogy is, suppose that this function is an object with a set of natural frequencies, and the e to the I omega x is a tone generator. Now as the pitch of the tone approaches one of the natural frequencies contained in this object, then the resonance between these two increases, and so that corresponds to the spikes. Okay, so that's the Fourier transform. Now, one important aspect about it is that it is invertible. So if we take the inverse of this function, we get this function. So here's the inverse function. It's quite similar to the original, but the cool thing about this is the Fourier transform can be manipulated, so we can manipulate the frequencies independently of each other. So for example, here I've diminished the second higher frequency, and because it's invertible, we can say, okay, what function would have produced this plot? And it turns out that it produces a very similar plot, just without that second set of oscillations. And so this has a lot of really cool real-world applications. For example, suppose you want to record a video for a surf presentation, but you live in Trinity Hall where the air conditioner makes a low rumbling noise. It's pretty annoying. Well, you're in luck though, because all you have to do is take the Fourier transform of your audio file, diminish the unwanted frequencies, invert the transform, and you're left with the original audio file just without those unwanted frequencies. Okay, so we still really haven't answered our original question, which is how do we get from position over time to frequency over time, because the Fourier transform takes us from position over time to magnitude over frequency. And if we were to take the Fourier transform of that audio file that I played in the beginning, we wouldn't see the different notes at different times. We would just see, I guess, all the notes at once, and all on the same two-dimensional plot. Well, the solution is actually pretty simple. We can split the audio file into a bunch of little segments at different times. We can take the Fourier transform at each of those times for each of those segments, string the transforms together in the same order that the segments were taken, and we're left with what at each time, what frequencies are present. And so I was actually able to replicate this. I used a little audio file of a clip from one of a canticle of Hildegard von Bingen, and so I'll play it for you, and you can kind of trace the sound, trace the pitch as it goes, as we progress through the audio file. Alright, so now I think we have a pretty good idea of some of the applications of the Fourier transform. But what about in modeling sound? Because we know that if we have periodic, continuous audio data, the Fourier's theorem states that that can be represented as a sum of sines and cosines. So for this project, I've actually decided, instead of using a linear combination of sines and cosines, it's better just to allow for a shift in phase and use just sine functions. And that seems to me easier to fit into a curve fitting algorithm. And for this case, we'll use the least squares regression. Now, for many functions, they're relatively insensitive to the starting parameters we feed into a curve fitting algorithm, such as linear functions, quadratic functions, even exponential functions. But for periodic functions, there are many local minimums other than the global minimums, as the least squares algorithm is manipulating the parameters. And so for this type of problem, we will need to guarantee that at least the frequency parameters start pretty close to the true frequency of the sample. Thankfully, the Fourier transform actually does just that, because it gives us spikes at the different frequencies contained in the samples. So here we can get a little more detailed. So we have our audio data coming in. We take the Fourier transform, which gives us this information, and we can actually count the number of spikes to determine how many terms in our equation we'll use. So for each of the spikes, as I said earlier, the magnitude corresponds roughly to the amplitude of the original function, and then the x-axis, of course, corresponds to the frequency. So we can feed those in for each one. We can take this whole thing, use the least squares regression on it along with the audio data, and that gives us an optimized function, which is actually pretty impressive when we plot it. And now this data here is me making the ah noise just for one constant pitch. We can actually hear the result in this next slide. So I'll play the original audio file. And here is the modeled audio. So a couple of things to notice. For one, this model was a lot more muffled, seemingly, than the original audio file. Now, this is because our model doesn't account for white noise that's contained in most, it's contained in human voice, simply. And we're really just modeling for what's the noise produced by the vocal cords, the kind of regular pulse produced by the vocal cords. So that's why it's a little more muffled. You probably also noticed a rapid clicking noise. Now that's actually because we're not modeling the whole sample at once. We're actually using the same technique as we used to create that three-dimensional graphic. So we're taking the original audio file, cutting it up into small segments, and then we're modeling for each of those and stringing them back together to produce our model. And now this actually allows, it turns out this allows for audio samples that vary in pitch and volume, and so it allows us to model more complex audio. But as we do attempt to model more complex audio, it turns out that oftentimes the frequencies obtained from the Fourier transform are not close enough, are not quite close enough. And so a way that I discovered to solve this problem is actually to repeat the last step multiple times, or at least as many times as we want. And so what we're actually doing here is, instead of feeding the whole audio segment into the least squares regression at once, we're basically forcing the clip to be small enough, the clip that we're feeding in to be small enough that the local minimum found is actually the global minimum. And so we can actually take the optimized parameters found from that, increase the size of the clip that we're feeding into the regression, and then perform the least squares again. And with baby steps, we're I guess building a more robust model for each segment. And so we do this as many times as we want, and it turns out this actually works a lot better. And so we're able to model more complex audio files, as I've done here. So here you might recognize this audio clip from The Lord of the Rings.
Looks like meat's back on the menu, boy!
And so a couple things to notice. So a lot of modulation in volume, in pitch, and even in vowel sounds. So theoretically, this is a lot more challenging to model than just a constant pitch, one vowel sound, relatively constant volume as well. So here I'll play the modeled version. So I don't know how impressive that is to you. I think it's pretty fun.
Looks like meat's back on the menu, boy.
So obviously there's still a lot of clipping, and it almost sounds pixelated. But there are a couple of ways that I haven't had time yet to totally get into, but a couple of ways we could improve this model. One is we could actually, instead of using constant parameters, we could fit polynomials to the different frequency and amplitude parameters found throughout the sample, and that would actually smooth out our sample, so we wouldn't have any clipping between little segments, and it would actually give us a lot more control over the sample once we've recorded it. Another improvement we could make is actually constructing a model for white noise. Now this likely wouldn't use a least squares regression, but we could sort of analyze, we could do a Fourier analysis for some of the white noise once we've modeled the noise coming from the vocal cords, and this would also just improve the realism of the model. But for now, that's all I have, and so I just want to thank you for your time. Thanks for watching.